Okay, it's now, it actually is now doing this.
Yeah, well, because they're all parked.
And I can pause it right. Okay. I mean, red seems to me stop. Okay, if you ever see that, then I am recording. And if I click on that, I'm actually, oh man, the camera's pointing at me. I was going to, there we go. Remember those "you are here"? You are here. And what's here? Periodic table, molar mass, formula weight, atomic mass, gas laws, math. In other words, that's what you brought here. And you're going here. Okay? That's where you're going. So you'll see that some of the things we mentioned today aren't even mentioned in chapter 1. Okay? So we're going to just kind of, and it's probably going to be a lot of review. Oh, by the way, I got 3 things. I don't know if you will get, this is your first homework assignment. Here are the slides. And I was telling Dominic, anything I do right now, don't assume that I'm setting a precedent for all future situations, okay? If I decide to start posting these and let you pull them up on your, I will do some of these things as soon as I get conversant with it. But, so yeah, if I was able to get these posted on Moodle, then you could pull them up on your laptop or whatever, or your iPad, and work on them, download them, whatever, okay? All right, so there's about 25 slides here. I'm going to flip through a bunch and then slow down in the last 8 or 10. But just quickly, we're going to, let me make a comment. Why do we start with gases in PChem? Why the ideal gas law? And you may have caught this from chapter 1. On Monday, I said we're going from simple to complex. Okay? Ideal gases, we have simplified it. There's no such thing as a perfectly ideal gas. But in order to deal with it, we're saying, okay, we're going to deal with gases. They're individual particles. There are absolutely no interactions between them. They have totally elastic collisions. So when they collide with one another, there's no loss of any momentum or energy. It's completely conserved. It's an ideal behavior. So they're kind of working as individual, independent entities with almost no forces on them except the temperature and the energy that they're absorbing from the temperature at which they're at. All right, so that simplifies things. And so then we're going to say, okay, well, what if the gas isn't ideal? What if it's a real gas? And then you move on into van der Waals equation, and then you start doing some other things from there. So that's kind of why we're starting with gases. So some of the concepts are going to be a little bit easier to navigate with that. When you get into liquids, and then you get into solids and crystal state, there's all kinds of stuff going on. The atoms are much closer to one another. There's a whole lot more interactions, and it gets a little more complicated. And the mathematics, the statistics, statistical mechanics gets heavy. So that's kind of why we start with gases. So here are just, in terms of elements, the blue are the elements that exist as gases at 25 degrees C in 1 atmosphere. Now that's not STP. Remember, STP is standard temperature is 0 degrees centigrade, or 273 Kelvin, and 1 atmosphere. But this is kind of at room temperature and at a standard pressure. These are the elements that exist as gases. And then, of course, there are other. So there's some elements. Here's some compounds that are gases. And yeah, keep in mind which ones are diatomic when you're dealing with molar masses and things like that. And then, well, pressure. Pressure is a critical thing to be able to measure and understand the units of in terms of gases. And a bunch of different other units. You know, 1 atmosphere is equal to about 14.7 pounds per square inch. So there's a number of different bars. The table in your book has a value for in bars. A barometer measuring that. Atmospheric pressure, we're talking about 20 miles of air. By the time you get up to 20 miles, the atmosphere is so thin that they don't consider you're kind of at the end of the atmosphere. So 20 miles of air, but you go up 4 miles, so 1/5 that, 20% of the way up, and you're at half an atmosphere because the air is thinning as you go up. Just some quick things. The barometer. Mercury is used as the liquid, kind of an odd unit. Millimeters of mercury is a pressure unit. Yeah, because it's based on this Torricelli barometer. Millimeters of mercury seems like an odd pressure unit, but 1 atmosphere of pressure will support 760 millimeters of mercury. Just quickly, some of the laws, the key laws. Boyle's law. If you double the pressure, you have the volume. All right, looking right here. You just look at those two examples right there. 1 atmosphere to change it to 2 atmospheres, keeping the temperature constant and keeping the amount of gas constant, you have the volume. And that gave rise to Boyle's law. PV, pressure times volume, equals a constant. Or pressure and volume are inversely proportional to one another. Pressure times volume is a constant. Charles' law. We are doubling the temperature. And what are we doing? We're doubling the volume. So now we have a direct proportionality. Increase in temperature increases volume. Charles' law. And so volume divided by temperature, and the temperature has to be in Kelvin, okay? Hopefully you remember that from your gas law. This is all pretty much review. But the temperature always has to be in Kelvin with gases, because it's only Kelvin that's proportional to the energy. All right? The amount of energy that those gas molecules has, it's not proportional to the temperature in centigrade or Fahrenheit. Those are arbitrary temperature. They're based on water, the properties of water. But Kelvin is an absolute temperature. It's 0 Kelvin, 0 energy. All right? So you're starting at 0 energy and moving on up. Temperature and energy are not identical, but they are proportional. The amount of energy is proportional to the temperature in Kelvin. Okay, so volume over temperature equals a constant, another constant. Avogadro's law, the balloon. The balloon, and The other balloon is back in the office. But when I blew up that balloon, I filled my lungs with air, I blew it up, it got to a certain size. I took another deep breath, blew it up, it got bigger. So what? The volume of the balloon was directly proportional to the amount of gas. All right? So a volume over, and normally we're looking in moles, is a constant. Where V1 over N1 equals V2 over N2. So those are the three. So if you put those three laws together, you got pressure times volume equals a constant. Volume divided by temperature is a constant. And volume divided by the number of moles is a constant. And we come to the ideal gas law constant. All right, so just keep in mind that you may know the ideal gas law as this, which is a good way to remember it. But if you divide both sides by NT, and you get the representation I have above there, PV over NT equals R, you have all of the critical laws in here. Should make that T a little nicer. All right, you've got, Boyle's law, Charles' law, Avogadro's law. So really, when we talk about the combined gas law, it would be better, this is the ideal gas law, but this is combining the three major laws together into the ideal gas law. Okay, PV over NT equals R, or PV equals nRT. All right, and what you have to pay attention to, you got to pay attention to what R to use here. Table, I forget what it was, 1 point something, 1.2. Table 1.2 in your book has R, values of R, a whole bunch of values of R. This liter atmospheres per mole K, liter bars per mole K, calories per mole K, joules per mole K, and liter torr per mole K. You got a whole bunch of, there's probably more than that, but that's a pretty good list. I'm looking at that 0.08205. Okay. Yeah. Liter atmosphere. One of the. Oh, I see. This is 0.0821. 0.08205. Got a homework problem. I hope I have that. Got it in here wrong. We'll have to change that. Got it in with a 6. I knew something was funny. We'll change it when I hand it out to you. All right, so you need to, this is where dimensional analysis comes in to make sure, and if you look at R and you look at the units of R, that's telling you what units your pressure, your volume, your moles, your amount of gas, etc., your temperature has to be in. All right? So, and carry those, I carry those into calculations. When I set up the calculation, I carry those units. I don't just write in 0.08205. I write in these other values. Okay, one thing I don't think I've got, I'm not sure if I have in these slides, is Dalton's law of partial, yeah, we get to Dalton's law of partial pressures here in a minute. Let's just mention a thing about density. You'll have a problem in your homework assignment. It's going to have you kind of assimilate some of these things. You know density. Density equals mass over volume. you got the ideal gas law. If we look at the density of gases a little bit, so density equals mass over volume. Let's see. Let's see how we got to this. Mass density equals mass over volume. Yeah, let's see if we can derive that a little bit. So let's say we have these two. P V equals nRT, and we have density equals mass over volume. So we got N here, we have mass and volume here. Probably the third little thing we need right here is that N equals the mass divided by the molar mass, right? So let's rewrite this. PV equals, so N is, all right, the mass of the gas divided by its molar mass is the number of moles of gas. So we can actually substitute that right in here. Like that. This is a kind of a capital M. I'm not sure the best symbol for molar mass they're using on this slide is the capital M.
You also use that for molarity, so it's
Well, molarity is,
normal.
yeah, like that. That's why I'm kind of trying to write a scripted capital M. That's what I'm trying to do there. Let me see, what else do we know? We can rearrange density equation so that volume equals mass divided by density. Right? Let's see, where did we get to here? So P I'm working on deriving that equation right there. The density equals pressure times the molar mass times R over T.
So when you plug density, well, oh, I see. You solve for one. Never mind.
Yeah, I'm molar mass equals density by RT over P. Molar mass of the gaseous substance. Density calculations. Density equals, let's see if we can get there.
I think I got it.
What do you got, Grant?
Okay, so
Or Ryan?
if you have P, I'm Grant. If you have PV equals
You're Grant. You're Ryan.
I'm Ryan.
You're okay. Well, let's see here.
Let me just write it up there.
Ryan and Grant. Yeah, go ahead. Go ahead. So what we're doing, we're going to this equation.
Can you see this, Liz?
Yep.
nRT. Then we know that V is equal to M over D, and N equals M over M.
Yeah.
So then we can get P mass over density equals mass over molarity RT.
I need to give you a better marker.
Then those masses can cancel out.
There you go.
And then what form was it in? It's just
Oh, so you
that.
got P over D
So this is
equals
P over D.
RT over M,
Yeah.
okay?
Okay. So then we wanted M, so you just multiply that over, divide this over, multiply this over.
We want D
We wanted
equals,
D. Oh, we want the top one.
we want D, so D.
Yeah, so I can multiply this over and then divide that over.
Okay.
So D
Okay.
equals, multiply that over. So P over M times RT. Big.
And, they got their M, no, this M comes up into the numerator, right?
When you divide by 1 over something.
Wait,
it
you
would
multiply
go
that
up
over?
to the
Yeah.
numerator, yeah.
Okay? And
I
you
was
get the
confusing
RT down there.
myself.
Okay,
There.
all right.
Do we have to know how to derive this? Helpful.
Well, to get through this, yeah, good. It's going to be helpful on one of the homework problems to be able to move around through these three equations. To move around through density, well, the three basic things you know. You know what the moles are, it's the mass divided by the molar mass. You know what density is, it's mass divided by volume. And you know the ideal gas equation, PV equals nRT. All right? So yes, if you want to copy that down, and obviously I was getting lost in the weeds here a little bit, but good. And this didn't fill all of that in. So yeah, I think to manipulate between those three would be helpful. And then, let's see. This second equation is just a rearrangement of that equation. Simple rearrangement of that equation. So the molar mass is the density times the ideal gas law constant times temperature over pressure. All right? And density, you need to get the density in grams per liter. So if I gave you a density, I told you to bring your calculators. You all got them? If I gave you a density, let's say the density is 4 point, I'm just going to throw a number out. We might end up with a density that's really crazy. Let me see. I want to try to come up with a density that's, let's say the density is 2.79, that's a 9, that's not a G, kilograms per cubic meter. Okay? So take just a minute and convert that into a density in grams per liter. And just to use dimensional analysis, how we doing? Pretty much there?
Yep.
Okay, so we're starting with this. And there are 10 to the third grams per kilogram. All right, so that gets us to grams. And there's 10 to the minus 3 liters, or no, cubic meters per liter, right? So really, these are canceling one another out. And you're right, a liter, I heard someone saying it, is 10, it's 0.1 meters by 0.1 meters by 0.1 meters, or 0.001 cubic meters, or 10 to the minus third cubic meters. Right? So you put this in, we don't want our liters to cancel out. We want our cubic meters to cancel out. And we go from 2.79 kilograms per cubic meter to 2.79 grams per liter. Okay? And why do we need to get there? Well, because molar masses are going to be in grams, and our PV equals nRT is generally going to be in liters. So if you get a density given to you in kilograms per cubic meter, you need to get it over into these kind of units to get there. Okay, we're not going to do this problem, but some of these slides, if some of these slides are in there to warm up or do some warm-ups. Calculate the density of carbon dioxide in grams per liter at 0.990 atmospheres and 55 degrees centigrade. So you would jump in there with these equations, with the ideal gas law, and you could calculate the density of carbon dioxide. Here's one that would warm you up a little bit more. A chemist has synthesized a greenish yellow gaseous compound of chlorine and oxygen and finds that its density is 7.71 grams per liter at 36 degrees C and 2.88 atmospheres. Calculate the molar mass of the compound. Yeah, calculate the molar mass of the compound. So you could use some of these to move on into that. Let's look at, here's another one. Let's look at part of it anyway. Chemical analysis of a gaseous compound, and then a lot of this is going to be refreshing your memory on Gen Chem kinds of problems. Chemical analysis of a gaseous compound showed that it contained 82.8% carbon and 17.2% hydrogen by mass. Now you've got a temperature, a volume, a pressure of the gas, so you could get to the moles of that gas. If the mass of the gas at this volume was 0.818 grams, so you have the mass, you know the moles from the ideal gas law, and we'd be assuming ideal behavior. Calculate the molecular formula. Well, why don't you take a minute right now, think about this, just this information right here, and how to calculate the empirical formula. We've got a compound that's 82.8% carbon, and it's 17.2% hydrogen. You remember these problems? And how do you simplify this problem?
Say that you have 100 grams.
Okay, you assume you have 100 grams of this material. And what does that do for you? Immediately that says, okay, I've got 82.8 grams of carbon. and I've got 17.2 grams of hydrogen. Now, go ahead and figure the empirical formula of this gas. So there's a couple parts to this problem. This would be the first one. The real question is, what's the molecular formula of the compound? But the first place to start is, what is the empirical formula? What is the lowest ratio of carbon to hydrogen in this compound? So how many moles of carbon is this? Six 6.9. Give me three significant figures.
6.893. 894.
8, 9. So 6.893, we can round that off to 6.89. And hydrogen?
17.06.
What is it?
17.06.
Wow. Okay. 17.06. Is everybody agreeing with that?
Yeah.
Okay, so we have this molecule, or we have this empirical formula. So now, how do you get that to integers?
Divide by the smallest.
So divide by the smallest. And what do you get when you divide this by that?
You get, well, carbon's 2.5 and hydrogen would be 1. No,
Other
other way around, sorry.
2.5.
Okay, so then where does that get you to? Multiplying by 2?
Yeah.
So C2H5. And that's your empirical. That's your empirical formula. All right? Well, without going through it, someone explain to me. Now the next part, we've got everything we need here with the ideal gas law to calculate what? Moles. So this part right here is going to tell us what N is. So now, I didn't leave myself a lot of space, but N, or this mass, 0.818 grams divided by N, is going to be the molar mass, right? All right, so you got enough information to navigate, work yourself through it. Well, you want to go ahead and do it. Go ahead and do it. Convert this to Kelvin. I didn't do it, so while you're doing it, I'll try to do it real quickly here. Yeah, it's 1.6. I'm gonna have to learn how to write on these slides a little better. They got stuff all over the place. Okay, let's work down through it one step at a time here. It'll just kind of reiterate what I've been saying about dimensional analysis and units, paying attention to units, which is going to be really a key part of some of these complicated calculations, more complicated than this. But our atmospheres are crossing out here. Our liters are crossing out here. Kelvin is crossing out here. And we end up with a unit of 1 over mole or mole. So we know that we're getting the right unit. Right, we've got a 1 in the numerator and 1 over mole in the denominator, and invert and multiply, the unit comes out as moles. What do you get? 0.0141, something like that. And then if you take that, 0.818 grams per 1.41 moles, you get a molar mass of something like 29.07 or 29.1 maybe. 29.1 would probably be good enough. Oh, no, I'm sorry. 58.01 grams per mole. Now the empirical formula, C2H5, gives you, what is the mass of that empirical formula? 29. And so the molecule is twice as heavy as that empirical formula. So we end up with a molecular formula of C4H10. All right? C4H10, that's molecular formula. And what else did it ask us? Is that it?
So that's just like a different way of finding, not using that equation that they gave. Like, we could have used the equation that they gave us and plugged everything in and
Well,
not solved from the.
We weren't given density.
Oh, well, you could have calculated it by grams over liters in the last part.
Yeah, if,
I did all in one line.
You did it all, yeah, you could have done it another way, but yeah.
Yeah, yeah.
I did it this way too.
You
but
didn't really need
that
to
felt-
pick moles.
okay, so you were working off of density. So you calculated the density of this
You
gas.
do
and-
density
Okay,
first and-
okay. Okay. Yeah, you could do that. I stuck with the more fundamental equation, the ideal gas law. But that would be fine. You get the same answer. Okay? So yeah, that just mentions a couple of things here and how to get an empirical formula, etc. Okay, I think this is the last slide. This is actually one of your homework problems. Actually, a little bit more than that. Oh, no. Are there more slides?
Yes.
Oh, okay. I'll tell you what, this is part of one of your homework problems. So don't worry about this one. You'll do this one on your homework. It's pretty straightforward. In your homework problem, I have gone up to a little bit more significant figures on all of this. All right, that's pretty straightforward. The ideal gas law. All right, let's mention Dalton a little bit, and I'm going to give you the homework, have you look at it, and it will be due Monday. Yes.
On the homework and stuff, is there a certain amount of digits you want us to have on our answers?
I would like you to pay attention to the number of significant figures in the information you're given,
Okay.
and then try to report your answer to the significant figures that are appropriate.
Okay.
All right, so in some of these problems, if it says that the mass was 0.818 grams, you got 3 significant figures, then you're limited to 3 significant figures in your answer. If I give you 4 significant figures, then move on up to using, you're going to see this, Kelvin equals centigrade plus 273.15. There's sometimes, if I gave you a temperature equals 35 degrees centigrade, then it's just centigrade plus 273. All right, you don't really have enough significant figures here to carry it out to there. So this kind of, to the best you can, I don't know how particular I'll be about significant figures, but try to be appropriate to the level of accuracy of the information you're given. If you're given things to 5 significant figures, then go to that.
I don't think there's class on Monday.
Or you're right.
Oh.
So this isn't going to be due till Wednesday. You're right, there's no class on Monday.
Whole week.
Wow, got a whole week to do the first homework assignment. Friday, I'll see if we'll hand out that second set. We'll just see. We'll just see where we're at on Friday. All right, let's just mention Dalton's law of partial pressures for a minute. It's one law we skipped over. Some of your homework problems are going to touch on this. Okay, again, we're talking about ideal gas behavior. We're saying that these gases, they're made up of discrete atoms or molecules, depending on what it is, if it's helium or if it's nitrogen, diatomic nitrogen. We either have atoms or molecules, but individual independent entities. They are bouncing around inside the volume. The pressure is a result of them colliding with the sides of the container. All right? So this gas generates a certain pressure, P1. This gas generates a certain amount of pressure, P2. And the total pressure, I don't know why this is coming. So so faintly. Can you see there's a P1 there?
Yeah.
P1 plus P2. I must have got a color that didn't come out very well on anything here. All right, so the total pressure is the sum of the individual pressures generated by each gas. So this is for mixtures of gases. Dalton's law of partial pressures. Okay, so now if you move from there, so you had gas A and gas B, two gases in a container. PA is the moles of A times RT over V. PB is the moles of B times RT over V. RT and V are going to be the same for both of these gases. They're at the same temperature, they're confined in the same volume. All right, so the total pressure is the sum of those two. This is the mole fraction. So the mole fraction for gas A is the moles of A over the total moles. And the mole fraction for B is the moles of B over the total moles. So PA is XA times the total pressure. PB equals the mole fraction of B times the total pressure. Here's your general equation. Your partial pressure for any particular gas in the mixture is its mole fraction times the total pressure. This same thing would work if you had four gases, three, four, five, however many gases you had mixed together. Again, assuming they're not reacting with each other, they're not interacting with each other in any other kind of forces. This would be ideal behavior, but a way that you could figure these things out. All right, here, this problem is giving you the pressure, and it's giving you the moles of each of these gases. You got neon, argon, xenon. You can fairly straightforward, you can get the N total, and then you can get the partial pressure of each one. The mole fraction, the mole fraction is going to be the moles of neon over N total. You get that mole fraction, and fairly straightforward application of that previous equation. Later on, we come to a chapter where we really delve into kinetic molecular theory, but just some basics. A gas is composed of molecules, atoms or molecules, that are separated from each other by distances that are far greater than their own dimensions. So that's what we kind of got out here. I mean, drilling down into the molecular level, you got these gas molecules moving along, but they're very far apart from one another relative to their size. The distances between them relative to their own size are very great. They're in constant motion in random directions. They frequently collide. They're not just colliding with the sides of the container. They're colliding with each other. Gas coming through the room, a perfume or some aroma coming through the room is bouncing along through all the air, the nitrogen and oxygen. So here's the ideal part of it. They exert neither attractive nor repulsive forces. When we start talking about real gases, we have to start dealing with this. What attractive or repulsive forces are involved? The average kinetic energy of the molecules is proportional to the temperature. Any two gases at the same temperature will have the same average kinetic energy. And that energy is directly proportional to its absolute temperature. It's probably the other thing it should be. So the kinetic energy is proportional to the temperature in Kelvin. Absolute temperature. Yeah, this is just summarizing some of the things that are going on. Boyle's Law, the pressure is proportional to the collision rate with the walls. Collision rate is proportional to the number density, or the density of the particles. And it's proportional to 1 over the volume. Pressure is proportional to 1 over volume. Charles' Law, pressure is proportional to the collision rate with the walls. The average kinetic energy is proportional to the temperature, so pressure is proportional to the temperature. Avogadro's Law, pressure is proportional to the moles of the gas, how many of these little particles are there that's colliding with the walls. And Dalton's Law, the total pressure is the sum of the individual pressures. Okay, real gases. See, as we get into van der Waals equation, I think that's where we'll pick up on Friday. So, there's a few slides here. We'll just introduce that equation. Van der Waals equation. You can basically see PV equals nRT, but the ideal gas law is being corrected for attractive and repulsive characteristics of these various gases. Let's take helium, a pretty ideal, or about as ideal as you can get. Pretty ideal gas. These numbers are very, very small. But you take water. Now we'd be talking about water at 200 centigrade or 300 or 400 degrees centigrade as a vapor. It has a very high A, minimal B value that's going to adjust this equation. Yeah, we'll pick up with this on Friday, and we'll do an example. You have some, you might dabble with it already in your homework. There is one. Let's take a look at this. For the most part, I didn't just list those 5 problems. If at all possible, try to do your work, and you can work it out on a sheet of paper, but try to fit it in here. And if sometimes there will be problems that are going to take a whole lot more room. There's just 5 problems. These will, so 1A, homework set 1A, 1B will be worth 100 points. Just about every assignment will be based on 100. And then these categories, homework is 30% of your grade. They'll just all go into there. And these are just to kind of have you reflect on what you have learned, basically use algebra, start applying these to the gas laws, and work down through some of these. So for problem number 2A is to just calculate the pressure as if it were an ideal gas, and then problem 2B is to do that again using the van der Waals equation. So if you want to wait, like you got till next Wednesday, we'll do the van der Waals. Look at the van der Waals equation and maybe do a sample problem in class on Friday, and then try to move a little bit further into chapter 1. All right, we got a few minutes if there are any questions. Yeah.
Did you say that there was something wrong with one of the questions?
Oh, yes. Number 1A, why don't you use 0.08205? That's what is in here. I don't know where I got that 6. In table 1.2, they have 5. Yeah, change it to 5. The R value. .08205. And I've worked out all these problems. Number 3 is the only one I gave you answers to. Friday, maybe I'll or in an email or whatever, I may send out some more answers. Okay, I've got them all worked out. I've got all the answers. But I thought I'd have you grind down through these without knowing where you are. All right, wondering, having a little bit of angst over it for these to begin with. All right? Great. No, good question. The grade book isn't set up yet, so obviously there's no grades in there. It is starting to get set up. So if you go and look at your grade, you might see something, but it may not be accurate until I get all these categories right.
Do you collect these and then return them before the exam?
Yeah, I'll do that. That'd definitely be what I'll be trying to do. So yeah, let's say this is due in a week, and go from there. Good. I'll see you Friday. Now let me get it straight again. Okay, I don't have it straight. But these things. All right, Ryan. Let's try something. Ryan.
Ryan.
Liz, Ryan, Grant. L-R-G. Liz, Ryan, Grant. Okay.
No, I know. Sorry, no, I just couldn't see your marker done.
It was dying.
I was like, I feel like this is kind of important to have written down.
Let's see, how do I stop this?